the medium one, and 6, because we had 3 on each end, 6 gummies for each of the sticks on that one. So, total amount of gummies, 28 times 2. We had 56 here. 56 times 2. We had 112 here. And 56 times 6, which gives us 336 here. Now, ultimately, we're trying to find the mass of the gummy bears. So the mass of the gummy bears would be multiplying these total amounts by the 2.5 grams. So 336 times 2.5 grams would be 840 grams. Medium density one had 112. 112 times 2.5 would be 280 grams. And then 56 times 2.5 would be 140 grams. So these are the gram amounts for each of the gummy bear masses. But remember, we have to convert them into kilograms, because kilograms is used for the equation. So dividing each one of these, there's 1,000 grams in each kilogram. So if you divide each one by 1,000, you'll get the value of kilograms. So if you do that for each one, it should just be a decimal point number of each one of them. Let me go ahead and move these back. So the mass of the gummy bears that we had for the waves on here, and again, you'll have to count it up on your own if you did your own wave and you're not using the data from this one, but we had 0.14 kilograms here, 0.28 kilograms here, and 0.84 kilograms here for the high density medium. And ultimately, that's how we can calculate our kinetic energy. Now we will have the velocity of the wave because of the 2 calculations we just did, and now we have the mass of the gummy bears for the wave because of that calculation we just did. So now we can ultimately plug those values into this equation here just by using a calculator, and then calculate the number value for each of these. And these are the things that you're going to have to look at to be able to figure out the answers on the next page, which are the analysis questions in the last part of this. And we'll just go briefly over some of the data that you probably should find based on the findings on here. You'll do the calculations and make your own determination based on that for the kinetic energy and the speed of the wave and everything. But ultimately, you'll have to go through and check that. And we're just going to go over the general answers right here in a second. Let me erase the rest of this real quick. Should probably just kept it all on. So, next page. So, draw a picture of your gummy bear wave and label the amplitude, wavelength, equilibrium, rest position, crest, trough, and medium density. If you were to draw your wave sort of, there we go. If you were to, oh my gosh, this thing. If you were to draw your wave all the way across there, and sort of label the different parts of it, and I'm just going to kind of show it as it bends all the way across. Whoops, there we go. That's sort of it spinning as it goes across there. So if you have your skewers on there, your wavelength is going to be the whole thing. Your equilibrium position is going to be this center line, which is where the duct tape is. Your duct tape is sort of your equilibrium position there for when they're at rest on there. So that part right there. Your amplitude is the distance that the skewer sticks off of each one of those. Your crest is going to be the point, the crest that we're using for the transverse wave is going to be the positive direction going down. And then your trough is going to be the negative direction coming down. But if you're looking at the actual skewers sort of travel across there, you could also label it as your crest being at the top here and your trough being at the top, at the bottom there. That's the individual crest and trough for the individual point particles. If we're talking about the crest and trough for the transverse wave that's created from the movement. You had the positive bump being the one that goes down and the negative bump being the one that comes back. And then the medium density. The medium density ultimately is all the gummy bears, basically. You could count the skewers too, technically, but the gummy bears that are on the ends there are going to be the medium density. So you'll have to draw the gummies on there and have those medium density bubbles marked on there, basically. Which wave traveled the fastest and why? Well, you can calculate your data on that to be able to double check and make sure, but pretty much you're just making sure that you're using for that one, which wave traveled the fastest and why, for number 2, and explain why in relation to medium density. How you're going to do that one, you're going to look at, oh my gosh, there we go. You're going to look at the which one traveled the fastest right here for the speed of the wave. So based on your calculations, you'll figure out which one traveled the fastest. And in relation to particle density, you're going to have to look at the low, medium, or high density in relation to that medium, low, medium, or high, which one traveled the fastest and why. Something you could look at for that, probably the mass of the gummy bears. The number of gummy bears in their total would ultimately affect the speed of the wave as it travels across there. So in relation to, I hate how this keeps on doing that. In relation to which wave is the fastest, explain why in relation to the medium density, what it's traveling through. Do it based on the particle spacing in between there. That's really what it's looking for. Which traveled the slowest, explain why in relation to medium density. Same thing. Refer to the speed. Oh, this thing. Refer to the speed, check the particle density, and relate it to the mass of the gummy bears on there. And then write a statement on how medium density can help or hinder a wave's motion or movement. And what you're looking for here, write a statement on the medium's density and can help hinder a wave's motion or movement. Basically, you're looking to see how... and then give a real-life example. You're basically looking to see an explanation of 2 and 3, how the medium density can affect the motion of the wave. And ultimately, what you should see is just a wave traveling through different spacings of particles. A wave is going to have a lot more trouble traveling through something with more particle densities than a wave trying to travel through something that has less particle densities. And you can see that pretty clearly. Take your window, for example. The light shining through your window comes through pretty clearly, but the light that goes through your sunglasses is diminished. That's because the light from your sunglasses is going to have more particle density, and it's going to have harder things for that sunlight to get through, while the particle spacing in your window is probably going to be far enough apart to be clear enough to allow that light to go through pretty much unscathed. Or the same thing as you're traveling through water. If you yell and scream in air, your sound can travel across that air pretty easily. But if you try to yell and scream in water, you're going to get a muffled sound because ultimately it's going to have a bigger particle density to go through. That's also why people can't hear as loudly through a door. You can yell and scream through a wall or a door, but it's not going to come through with the full effect. It'll be diminished of some sort. And that's because there's something in the way blocking it, which is the particle density that you have there. Which wave traveled the slowest and traveled the fastest, and explain why in relation to medium density is the big point that we're trying to get across for this activities, for what you guys did, for the data that you guys collected. So just analyze the data that you got and answer the questions based on sort of these different things. Ultimately, what you should be able to see, and I'll just kind of make a couple notes here before I end this video. Ultimately, what you should be able to see is basically that the higher the density gets... Is this even erasing? Let me do this. Whatever. The higher the density gets, as you get to a higher and higher density, you should see two things. As you get to a higher and higher density, you should see the speed of the wave decrease, and the mass of the gummy bears would be increasing because of the higher density at the bottom, and the kinetic energy of the wave should also have the same issue, basically. If the wave speeds decrease, the kinetic energy of the wave will be based on a combination of the wave speed and the mass on there. But ultimately, because of the particle spacing that it's traveling through, you'll probably see a decrease in the speed of the wave. And that's pretty much how you go through and do this activity. If you did not do the activity or you don't have good data to be able to use, just use this video and use the information on here to be able to make your calculations for your wave analysis data chart that you're turning in. Ultimately, what I want to see you guys turn in is just, have the wave data chart turn in ready for it, and then also the analysis questions ready for it. Feel free to write them on a separate piece of paper. Let me know if you have any questions about this activity. Otherwise, that's pretty much it. Go ahead and finish it up and turn it in.